Well, hello everyone. My name is Bruce Dominguez. Welcome to Remoticon. I hope you're having a good morning, good afternoon, or good evening, wherever you may be. And just FYI, you can always post questions or comments in the group chat and respond to each other, give each other feedback, because that's what makes this community awesome. And today we'll be joined by Matthew Alt. And he'll be hosting a discussion on hardware debugging. Matthew is a reverse engineer with a focus on embedded systems. He began working in the security industry for automobile performance and searching for vulnerabilities in engine control units and diagnostics implementations. Matthew currently works as a security researcher and as a trainer and consultant. And he regularly posts projects to his GitHub, wrongbod.github.io. And with that, Matthew, thank you for being with us.
Yeah, thanks for having me. I see some familiar names in chat from the Ghidra course. So those of you kind of know what you're getting into. As we go through these slides and work through what we're going to work through on the hardware bench, please feel free to ask questions and I'll get to them as soon as I can. And kind of like they said before, definitely open for, having discussions about this and, getting like a back and forth going. So with all that to say, let's get started. So already got an introduction, so we'll burn right through that. We're going to talk about like the overview and goals of the session, what, we want to try to learn, what we want to try to do. We're going to review, what single wire debugging is and do a few exercises on it. On the Xbox controller that we have over here. And then we're actually going to talk about DFU mode, which I know we didn't mention in the project, but found a nice little Easter egg with this controller while trying to debug something after I bricked it. And so we're going to talk about that, which is pretty interesting. And then if we have enough time, we're going to go over JTAG at a pretty low level and show how to use that on an SSD that I have here on the bench. And so, yeah, as they said before, I'm Matthew Alt. I post stuff under Wrongbod, and I'm a security researcher, so we already talked through that. We don't have to do that anymore. And so, yeah, the purpose of this workshop and this session is to explain to you how, hardware debugging works, and also show you how to interface with it using, open source tools, both software and hardware. And so as we go through this, we're going to take a look at two different targets, an Xbox One controller and a Transcend SSD, if we get enough time. And so what I want everyone to get from this, and what some of the takeaways I hope are that you folks learn how to identify these ports when you look at them on a PCB, and also understand kind of the core components that make up how a hardware debugger works. So the use case being, if you plug in all your tools and you hit the button and maybe it doesn't immediately work, I'm hoping that after this, you'll have an idea of where to go to figure out maybe how to tweak things to get things to work properly. Because anyone that's tried to use, OpenOCD or any kind of JTAG software, that sometimes there are quirks, sometimes it works, sometimes it doesn't, and it's kind of hard to get down in the weeds and tweak things and figure out how to make it work for your particular target. And so we're going to go through how to use, OpenOCD and your JTAG to look at some of these ports, and with the ultimate end goal of pulling firmware off of them, reflashing that, and then even doing, single-step debugging through GDB. So the first platform we're going to take a look at is an Xbox One controller. We posted a link to that up on the Hackaday IO page. And the goal for this, we want to extract RAM, flash, and rewrite that flash. And we'll talk about what protocols this target uses later on. The second platform, if we get a chance to look at it, is, I was asked to move my video up. Is that better? I can make it smaller too. The second platform is this SSD, and the goal of that is going to be to identify the JTAG pins, extract RAM via JTAG, look for any data of interest in that dump, and then take a look at how this thing behaves when you issue certain reset commands, because it actually has some pretty interesting features in it as well. And so this first platform, this Xbox One controller, I'm going to flip over to the hardware view real quick for those of you that have one, or those of you that don't, you can follow along here. So we've got this Xbox One controller. Now, as you can see, we've got, a couple of epoxy blobs here, probably covering the main CPU. if you look at it closely, you can see that there is a debug header right here. And I've got some header pins soldered to that. And in addition to that, we've got another IC here. We've got some pads for what look to be, you know, an SOIC8 chip. So whether that might be could have been an additional EEPROM or something, we're not sure. There are multiple test pads throughout this thing that are labeled, you know, with different buttons that they can press, or just, you know, TP and then a number. And so to give you a better view actually of the debug header, I'm going to put it under the microscope. Get that cable out of the way. And so bear with me, folks. All right, here we go. Yeah, so here's our debug header. Let me get that in better focus. Yeah, okay. So we can even see, looking at this header, that if you look at it mirrored, it would say SWD. And so some of these pins on this header are labeled. This one, the first one is not. And then we have res, A14, A13, and 3v3. And so those of you that have looked at, you know, this kind of hardware before, that's kind of an immediate indicator of something that you might want to start digging into. And so with that, let's jump back to the slides here. And so after taking a look at that, right, the core components that we see are, you know, this, what is probably the CPU that's covered in epoxy. We've got, you know, a labeled USB connection down here. There's this additional sound chip here. We've got, you know, this debug header that we just took a look at. And then these pads for, you know, what could be an EEPROM or some additional peripheral chip that may be used. And my hypothesis is that this was used for, the same design was probably also used for Xbox 360, where they had an additional chip that would actually issue a challenge response over USB to authenticate with the Xbox. So with that, you know, what can we infer from taking a look at this PCB? Well, we don't know what the CPU is, right? Because it's covered in this epoxy. So we're already kind of in the dark, which really isn't where we want to be as reverse engineers, right? You at least want to find a, you know, a part number or something you Google and grab a data sheet. But we're kind of already deep in the woods here. That AK495 chip is actually an audio processing chip. And so we'll go back real quick. That's this chip right here. And you know, when you're looking at a PCB like this, it's kind of easy, or it can be easy to infer, you know, functionality based on the location on whatever the target is, right? So we have the headphone jack right here, and then right next to that, we have this audio amplification chip. And so, as I said before, that other pad or set of pads is likely left over from, you know, the design for the Xbox 360 controller, most likely from this same brand that was used for this external authentication IC. And so this debug header that we identified, this guy right here, is probably our best bet, right, for learning more about, you know, how this target works or what components it might be used. All right. So if, you know, we can examine those header pins, and what can we determine about those from the silk screen, right? We looked at it, we saw that one of them was labeled 3v3. That's probably voltage. One of them was labeled RES. There's a really good chance that that is going to be used for a reset line, because it's pretty often when you have, you know, hardware level debugging, you're going to have a hard reset line somewhere near the pins that you're using for that. And so we can take a look at what this device looks like when we actually plug it into the Pi. So let's do that really quick. So I'm going to go to a terminal on the Raspberry Pi here, and we're just going to run dmessage and plug this controller in. So we plug it in. Okay, cool. So as one would expect, right, it just shows up as a standard USB device, typical HID device. You see we've got serial number, manufacturer string, and then the product description as well. Now you'll notice the manufacturer string is a little messed up, and we'll explain why that is a little later. So Matt, this is actually a custom image that I put together for the Raspberry Pi that presents itself as an Ethernet device to your host, and then you can go through and access these tools from there. But this is the same thing you would have if you were at just a terminal on the Pi. But having it accessible through the browser makes life a little easy. And so if we jump back. So if we look at the voltage levels across the 5 pins that we have. We have, the first pin, which we assume is probably ground, right, is 0 volts. The next pin, which is the reset line, is 3.3 volts. The third pin in the list is floating at 0.1 volts. The third is at 3.3, and the fourth is also at 3.3, which makes sense, right, because it was labeled 3.3 volts. And so when we're looking at something like this, right, you want to always make sure that you're aware of what your logic levels are and the logic levels of whatever it is you're trying to interface with it. And so we're going to be interfacing this controller with the Pi. They share the same logic level, so they're both at 3.3. So we don't have to worry about any kind of level shifting or anything like that. And so if we look at these pins, if we monitor them on boot with a logic analyzer, there's no data going across them. They just remain at the same voltage. And so the reason we would want to check something like that is because it could be, potentially a UART or some other kind of, debug console. And so, how does this thing present itself? Here's the same dmessage output. And so with that header that we looked at, it's not UART because we don't see, or it could be UART, but we're going to assume that it's probably not. It's obviously not SPI. We don't see like any clock lines or anything like that. And the interface is pretty much completely inactive. So what could it be? It very well could be, a 2-wire interface called single wire debug. And spoiler alert, that's exactly what it is. And so what we want to cover with this single wire debugging section is kind of learn what that is, learn how to identify it. We want to learn how to interface with it via OpenOCD, and also kind of how to, once we have the single wire debugging capability, if we still don't understand everything about the target CPU, learn how to identify what the CPU part number might be via memory reads and writes. And so once we have that, we're going to try to extract firmware from it and see if we can modify and understand this new firmware. And the last thing, if we get enough time to go through it, is to take a look at DFU mode and how we might interact with that. So to kind of jump into this, single wire debugging is a debug interface that's specified by the ARM debug interface specification, or the ADI. And some of you may be familiar with that. It's a pretty excellent document that walks through how ARM specifies these various debug peripherals to work. And so what single wire debugging does is it interfaces with something called a debug access port. And a lot of these terms kind of get muddled together, and I'm hoping through this talk we'll be able to kind of clear up what these different terms mean and what they all do. And so by accessing this debug access port, access ports, or APs, are read to and written from in order to actually read and write memory, or to interact with whatever internal peripheral you're trying to look at on the device, whether that be for system level debugging, or you're just trying to read and write memory, or you're trying to interact with some other peripheral like core side or something like that. And so we have DAPs, DPs, which are data ports, APs, which are access ports, and all of these things are kind of connected to one another, and the way in which they're connected is defined in the ARM debug interface specification. So if you just Google ARM ADI, you'll be able to find the latest version of their interface specification, and that's extremely useful for getting a handle on these things at kind of a higher level. And so the ADI is what ultimately provides us access to these kinds of debug ports. And so if you're familiar with JTAG, which kind of links the different taps together, or test access ports, single wire debug kind of abstracts those out into different components. Like we said before, we've got the debug port, the debug access port, and the access port. And so these things are defined in the ADI, and you can interact with them through multiple kind of physical mediums, right? So single wire debug is just the physical interface that we use to interact with the debug access port, which in turn interacts with the debug port and the various access ports. And again, I know that these terms kind of get smashed together when you talk about it, but we have some diagrams later that I think are going to help clear this up a little bit. And so the reason I like to go over this kind of stuff is because when you're reverse engineering something, you kind of have to break it down into the fundamental building blocks, right? Because that's all you have. We don't know who made this chip. We don't know how they interfaced with it. We don't know really anything except for that this might be a single wire debug port. And in order to understand how to interface with it from kind of a black box perspective, it's important to understand, how the core pieces work. And so starting with that is the DAP, which is the externally facing peripheral, right, that's accessed via single wire debug, or JTAG, or serial JTAG, like we talked about in the last slide. And so that consists of two parts. You've got the debug port and the access port. The debug port is by default always supposed to be there. So the debug port is kind of your ground truth. And so APs, or access ports, are what define all the different debug features and functionality that one of these chips might have. So if you've ever heard of, core site or any of the tracing features that a lot of ARM chips have, those are interacted with through these APs, which are communicated with via these physical mediums like single wire debug or JTAG, et cetera. And so when you're doing single wire debug, every transaction or every little thing that occurs is going to be sent to either the debug port, the DP, or an access port, an AP. And so let's talk about the debug port, right? So this DP contains various registers that you use to kind of monitor system state. You can use it to get ID information about the CPU. And this is kind of the piece that you always know is supposed to be there. This is what's defined in the spec. And so with the DP, you can actually read to and write from registers that are used to actually interact with the other APs. And so this is all, again, independent of single wire debug or JTAG or whatever physical medium you're using. But this is kind of the first thing that you start talking to when you go to access something at the kind of hardware level for debugging. And so access ports are really where kind of the meat is with hardware debugging. That's where we can get access to memory. That's where we can get access to external peripherals and things like that. And so these are accessed through the DP, as we mentioned before. DP is debug port. It's essentially a register that's written to. The debug port in the ADI is like a bank of registers that is written to. Yeah, so internally it may look like a bus, but really it's going to look more like a memory bank. It does not quite, one of the questions is, does it act as a router? It doesn't quite act as a router. You write to it exactly what you want to address, and it will fetch that for you. So it doesn't do it automatically. You still have to tell it what you want. So in a sense, it does route data, but as we'll learn later, the packet structure for single wire debug lets you access an AP directly. So you don't have to go through the DP. And so when you're looking at an access port, there's one register that's always used to identify the AP type. And we're talking about registers, we're talking about access ports, and you haven't even seen these things yet, right? These are all very kind of higher level ephemeral things. But what you need to imagine them as is just kind of like banks of memory or banks of registers that can be read to or written from in order to access various things that are internal to the CPU. And so there's two types of APs that are defined in the ADI. You've got, memory APs, which are used to access various internal memory buses. And so those of you that are familiar with VLSI, things like that, are, kind of understand that there are lots of internal buses that are being used within your CPU, and this will let you kind of read and write to those. And based on what capabilities the chip provides, you can use, these various memory APs that are presented to interact with this debug functionality, excuse me. And then there's the JTAG access port, which is used for kind of traditional boundary scan or, standard JTAG uses. So things for querying GPIO pins, things like that. And so as we said before, the memory access port kind of gives you a window into some kind of abstract memory system or memory bus, whether that is something that lets you, read and write directly from RAM, or something that's used to kind of interact with the debug unit of the processor. And so this is just kind of an overarching category that's used to describe these various access ports that you talk to through, single wire debug or JTAG or whatever your mechanism is. But at their core, these MEM APs are used to interact with the memory of the target CPU. And so, we've got these APs, we've got these DPs, we've got the DAP, and then we've got SWD. We've got so many acronyms here, it's out of this world. But how do we, learn when we're taking a look at like an unknown, let's say we're looking at an unknown port and we can, read from these DPs and these APs. We're going to learn how to do that later. But how do you know what data is contained within there? So each of these DPs and these APs will point to something called a ROM table. And this ROM table has information about whatever debug component you're talking to. And so that is what actually connects to that internal bus that's pointed to by your memory AP. And so each of these APs and DPs have dedicated registers that point to these ROM tables that are used to identify, what their type is and what they're used for. And I know this is we're throwing a lot of acronyms and a lot of definitions out. So if anybody has questions, toss them in the chat and we'll do our best to get to them. So yeah, we've got these three acronyms, right? DAP, app, DP. The DAP is kind of the entire overarching debug interface, if you think about it. The APs can provide access to like various peripherals or memory and internal CPU buses based on how they're designed and whether or not they're exposed. And the DP is the way that you access these things, initially. It's kind of the standard way. It's kind of the first step in the chain to access these various peripherals and buses. And so finally, what this ultimately ends up looking like is we've got this massive thing right here. This is the debug access port, right? And we can see that it contains the debug port, which is the first thing we read to and write to, the AP access, right, which talks to our memory APs. And then those are what, in this part to us, right, is kind of done without us needing to know anything. And that's why this is all, that's why this is all defined this way. So is the video blurry for everybody, or is it? Okay, I'm getting mixed signals in chat. I'm gonna leave it.
Sorry, Matt. The big screens, the larger screens seem to be fine. But if you went to a smaller, if you switched to, I believe some of the other graphics that you had where the text is really small, then that becomes blurry.
Okay.
I believe some other discussions and talks, they switched using the straight zoom video feed. So if you do, maybe consider that if there's more issues.
Okay,
but
I can do that for the terminal stuff. I'll try to do that and see if we can.
Okay, great.
We go back. But yeah, so I'll do what I can to make the terminal video a little less blurry when we get to that. So sorry about that. So this is kind of the overarching picture of what these debug ports actually look like. So you've got the physical connection, which is going to be implemented via single wire debug or JTAG or serial JTAG, whatever that might be. That then talks to the DP, which is the first layer that we can perform these AP accesses that we then use to kind of get access to memory or various debug peripherals. And the reason this is all abstracted away is that for various CPU designs now, all you need to understand is how to access these things right here. So the debug port and the memory APs. And that's kind of where the beauty of things, like OpenOCD and things like that come in. Because once you understand how to do this on some cores, it might carry over to other processors. And so the AP is accessed. So we got a question, how do we connect to an AP directly? You connect to it through either this physical connection, which is single wire debug, and then you can address the AP through packets that are sent to the debug port. And we'll go over what that package structure looks like here in a moment. And so, yeah, we have this first layer of physical connection, which is going to be your JTAG, your single wire debug, your serial JTAG, what have you. And then that talks to, our entire overarching debug access port. The debug port is the first stage of the process. That's how we kind of identify the target. That's how we get information about it. And then we can, through that, talk to these memory access ports, which give us access to, external memory and internal peripherals. And, one of those things that it'll give us is the ability to debug the processor. And so, we've got this physical interface, single wire debug. This is implemented with 2 pins, which is kind of why it's preferred over JTAG or why it was developed instead of JTAG. You've got, serial clock and then serial data in and out. The clock pin obviously is used to determine when you sample data on the single wire debug line. And the IO pin is bidirectional. So there's like a direction bit in the packet that tells you whether or not you need to wait for a read or a write to occur. And so when we send these packets to the DP or the DAP, it can be split up kind of into 3 parts. You've got your header, the response bit, and then data. And so the header actually determines the direction of the payload, whether or not the data portion is going to the device or coming from. And so here's a blurry picture of what the packet structure looks like. The the header part contains, start bit, a bit whether or not you're accessing an access port or a data port, which we just talked about, whether it's a read or a write, an address bit, parity bit, stop bit, and a park bit, or a turnaround bit. And then you'll get an ACK from the target, and then following that, you get the actual data that you care about. And so these are two examples of kind of a read and a write transfer. The thing to take away here is to understand that, we've got pieces of this that are used to access, the AP versus the DP. And yeah, the address field is 2 bits. And so that's the data field is eventually used to write to other addresses. So it gives you more than just a 2-bit address space. It's basically used to select whether or not you're at which AP you're going to access, if that makes sense. And so the packet header is pretty small. You've got 8 bits total, a start bit, the AP and DP bit, which basically determines whether an AP is getting accessed or a DP. The read and write bit, 1 is a 0, or 1 is a read, 0 is a write. The address bit, which determines the address of the AP or DP that we're going to talk to. And then, a parity bit, stop bit, and a park bit. And so this is used, the park bit is basically used as kind of a timer, or not a timer really, but an indicator of when the host can drive the line, because it's a push-pull line, or it's open drain line rather. So for example, to read, the ID code of a device over single wire debug would look something like this. So first we see our start bit, which is 1, right? We've got the access port or data port bit, which is 0. So we're talking to the DP. We've got read and write. So remember, this is 1, so it's going to be a read. And then the address here, which is 0, and then 0, because we're just talking to the data port with this, because we're trying to read out the ID code. And so data port read at address 00 is always supposed to return the ID code. So that's one of those ground truth things that you can use to figure out whether or not you're talking to something that's single wire debug. Similar to how with JTAG, you can try to clock out the ID in order to figure out if the target port's a JTAG port or not. And so for the parity bit here, we have 1, and then the stop bit, and then park, which is supposed to be 1. And then that gets followed up with an ACK from the processor, where it's a 3-bit field, and it can be either OK, wait, or fault. That's what they use it for. And so this is the processor coming back to us, telling us OK. And then it responds with the ID code. So this is the processor firing back the ID code after we have asked it to read from the debug port at address 0, and what it returned to us then is the ID. And so when you're taking a look at, what you think might be a single wire debug pin, or any debug port really, you're going to have most likely a VCC pin near there to either grab the logic level, or just to let whatever the target hardware is that's talking to it know what the logic levels is. And this isn't unlike what you'd see on a UART port. And it's unlikely that in typical usage, you're going to actually be able to see any activity over these lines, because they're designed to be talked to by a host. So unless there's something, on your target PCB that's actively talking to your CPU over single wire debug, you're not going to see any activity on these lines. Just looking at the chat real quick. I'm not sure if the slides are going to be shared, and I know the video is getting recorded, so I'm assuming that'll get posted at some point. And so the clock line usually utilizes a built-in pull down. The IO line usually is pulled up. Now that can change on different targets. It's not always ground truth. It's just kind of what is commonly seen out in the wild. And the other thing too is it's really commonly used and seen on STM32 MCUs, which I'm sure everyone in here is fairly familiar with. And so when you're talking with single wire debug, there's a fair amount of different hardware interfaces you can use. Some of them are provided by the OEM or the chip manufacturer, and there are also open source tools that you can use, like the FTDI chip. You can use the Segger J-Link, which isn't open source, but it's a fairly useful tool. There's things like the Fly Swatter that people can use, And again, most of the time when you get a microcontroller, you get something from an OEM, they provide their own hardware solution for it, or just implement it over USB or something like that. Or yeah, like a Blackmagic probe, like someone's mentioning. And typically OEM tools will also come with their own software suite for talking to these things. But as a reverse engineer, you're not going to have access to all that most of the time. There may be cases when you will, and that's always great, but it's kind of always best to assume you're going to have as little data as possible. And so with the Raspberry Pi, we can interact with a single wire debug interface using OpenOCD and telling it that we're using a single wire debug interface. So there were some config files that were shared in the chat if people want to take a look at those for if you're ever going to use OpenOCD with a Raspberry Pi. And so you define in the config file the various JTAG or the various single wire debug pins that are going to be used. And so what I'm going to do is connect to the header, and for A14, I'm going to connect that to pin 2 of the Raspberry Pi, the GPIO. And for GPIO 3, we're going to connect that to A13. So I'm going to switch over to the hardware view real quick. All right, hope everybody can see that. All right, so we're going to connect up to these first 2 pins. This first pin, after looking at it with the multimeter and doing a continuity test, is ground. So we're going to ground that. And then the next 2 pins, 14 and 13, like we said, we're going to connect them to 2 and 3 on the Raspberry Pi. So pin 2 and pin 3. And so, fairly straightforward, just 3 lines, which is nice for us. And so we've got that connected to our Raspberry Pi. Now I'm going to switch back over to the terminal, and we will figure out the issues with resolution. So bear with me here, folks. So here's our terminal. Is this too small? Can people read it? I can make it larger. Okay, I'm getting positive feedback here. So I'm gonna leave it with this. Yeah, so apologies for that, folks. Hopefully this is doable. And I think this is the max, unless I can, yeah, this is as high as I can go. All right, so we'll take a look at an initial, what the config file looks like. So just so you're familiar, and this was shared in chat. So first thing we're going to do, we tell OpenOCD, which presents an interface to us over Telnet. We're going to tell it what port we want it to present to us. We're telling it, hey, use the adapter driver for the Raspberry Pi. That's what this BCM2835 GPIO line is. And this is for the Raspberry Pi 4, this peripheral base address. This basically is telling it, what the base address is for interfacing with these GPIOs. And then we have, speed coefficients, which we're using to calibrate the clock speed for how quickly we're going to interact with this target. And then we finally got our GPIO numbers here for clock and data in, data out. Now you'll notice, right, that it's not the header pin number, it's the GPIO number. And this works on various revisions of the Raspberry Pi. The only thing that'll change will be this base address. And they have example config files in OpenOCD for you to use. And so we're going to tell it to use, speed of, we're going to go 100 kilohertz, and we're saying for the transport select, which basically tells it the physical interface that it's going to go over, we're saying use a single wire debug. So we're going to pass it RPi single wire debug config. All right. And so the first thing we see, it's telling us, all right, for Tickle connections, port 6666, for Telnet, port 1337, we're using the bitbang driver for the Raspberry Pi. And then, so yeah, let me see if I can make this video any more clear for you. Yeah, I've got the HD box checked, so I'm not sure. So yeah, I think this is probably as good as it's going to get as far as video goes, folks. So we've got, the first error that we get, and I chose 100 kilohertz here just to keep things relatively slow. You could go higher if you want. You could go lower, I guess, if you really wanted to. But for the Raspberry Pi, this is always a good happy medium. I've had some issues with going, trying to go too high with doing single wire debug on targets that aren't really, expecting it or necessarily designed for it. So this has always just been kind of the sweet spot. And so it's telling us here, right, the big thing that we're seeing is it's saying GDB services needs one or more targets defined. And so with that error, I'm going to take you back to the PowerPoint. And so we filled in the GPIOs to match the target wiring. And there was originally a missing value for transport select that we added, telling it basically, hey, we're going to be using single wire debug as the transport mechanism. And so here's what that looks like for those of you that maybe couldn't see it on the terminal. And so we're getting this error, right? That's telling us, hey, I see that you've defined all the parameters of the physical interface perfectly fine, but I need to know what target I'm talking to, right? So that's basically what it's telling us. So now we need to define, a DAP that we just talked about. So with OpenOCD, you can define a new DAP with, SWD new DAP. You give it a name, tell it what kind it is, and then tell it to enable it. And then we actually create the DAP from the thing that we named here. And then now we give it a target. And so I'm going under the assumption that this is a Cortex-M. So, we get a lot of questions like, we know nothing about this CPU, right? We don't know the architecture. We don't know anything. What we do know is that presumably we're using a single wire debug interface. And with that, we know that STM32 uses those pretty regularly, and so do a lot of other kind of like COTS ARM chips. So just as a start, we're going to guess Cortex-M, or we're going to start with, kind of a more common chip. And this is, an assumption. We'll find out that it's a fairly reasonable one. So if we look at the Xbox One config, which is just that same config file you had before with the DAP defined and the other components defined. So if the assumption is wrong, we got a question. If the assumption is wrong, it's not going to be able to properly identify the chip. So if we chose, MIPS or something weird like that, it simply just wouldn't work, right? And again, a lot of this, when you're looking at, an undocumented debug interface with a chip that's covered in epoxy, there's a lot of guesswork that goes on. And I've obviously streamlined that guesswork because we only have so much time here, right? So when I was going through this the first time, I'm basically, you're basically, you're guessing different architectures, you're trying to figure out what it is, and you burn a lot of time doing that. So let's see what happens when we run OpenOCD with the DAP defined. All right, so right here, right, we see a lot of the same stuff we saw before, but we've also got single wire debug, data point DP IDR, so data port ID register, and it's spitting back like a proper ID. And so by reading the info that's defined in the data port, it's able to tell us that the CPU has 6 breakpoints, 4 watch points, and it's spinning up, a GDB server for us, and as well as the Tickle server and the Telnet server. So we're now able to query, or OpenOCD is rather able to query the DP, get the ID, and get some information back about the chip. And so for those of you that couldn't see on the terminal, hopefully this shows up. You see we get the DP-IDR here, which is the identifier for the chip. And those of you that have looked at these before probably immediately know that that's an STM32 series chip. So this was a response that was given to us by the DP when OpenOCD tried to enumerate the target. And so now that we have this DAP, we can go through and initialize it with the init command. This will go through and kind of initialize all the registered DPs and APs that it can find. And then once that's done, we can print out the info that OpenOCD is able to query. So let's take a look at that. We're going to go back to the terminal. So sudo OpenOCD-f expo.config. All right. So if we go into another terminal, we connect to that with telnet. So we do init, and then we'll type in dap info. Now this is going to be tough to read because it's a lot of data. So hopefully we can follow along here. If we scroll up, we can see here it gives us the ID register, right? And then we see it goes through and reads the MAP, so it grabs the base and then starts reading the ROM table. And so immediately looking at this, right, we see that one of the peripheral IDs and the designer IDs for ST microelectronics. We have the part number, which is hex 411, and then when we look at this additional ROM table here, this peripheral address, OpenOCD is able to go through and query that and read it out and figure out, okay, we can see that it's a Cortex M4, which is great. Coincidentally, obviously not a guess. It took a fair amount of time to figure that out initially, but if you were looking at this and you had the wrong architecture identified and you could read through the ROM table, you would see that this is a Cortex M4. And so you would be able to get to this data regardless of what architecture you provided it, which is kind of nice. And that's how I found it to begin with. So you ask OpenOCD to grab you this DAP info. And here we can see we have a couple of different ROM tables that are telling us what the different APs are used for, right? So we have one for flash, patch, and breakpoint. We've got one for data watch, point, and trace, system control space, etc. And so these are all the different peripherals that we can interact with via SWD. And so we talked before about like there might be trace modules involved. We've got this trace port interface unit. And this is where, reading through things like the core site specification and stuff like that will come into, excuse me, will come into play. And so now with that out of the way, we know that it's an ST microelectronics chip. We know that much, right? It's telling us right here. It's giving us the part number, which is unrecognized. This isn't always something you can go off of, this hex 411. But the big takeaway here, right, is that we know it's a Cortex M4 because we're seeing that in the DAP table, and we know it's in a ST microelectronics chip. So when you start to kind of piece all that together, right, it's an ARM-based ST chip using single wire debug. Good chance it's an STM32. But there's other ways we can figure that out as well. And so to walk through that, we're going to go back to the PowerPoint. Okay. I'm sorry, I'm getting right back. I'm getting to these questions now. So if the architecture was wrong, yeah, we would still get the ID regardless of the architecture. Debugging and things like that are what would probably not work. And yeah, the info we were looking at earlier was from the ROM table. And yeah, so hex 411 doesn't exactly mean STM32 411. It's just it's just another ID field that's used. Sorry, I'm trying to get to these as I can here. So yeah, we took a look at the DAP output, and we could see things like ST microelectronics, we got a part number, we got the architecture as well. And so we're going to move forward, assuming this is probably an STM32 chip of some sort. And so these are extremely popular ARM Cortex, microcontrollers. They typically have, the Cortex CPU core, SRAM, internal flash, and the debug interface / other external peripherals. I'm assuming everybody here is fairly familiar with the STM32. It's an extremely popular chip. And so this chip also utilizes the SWD interface, which is good for us. And so these CPUs store identification info in various memory regions, right? And so at this URL, which I can post in the chat, basically they have different regions of memory that you can read from to get CPU ID information. And so by doing that, you can try to, now that we can interact with this AP, we have the proper architecture figured out, we can go through and try to read from these memory regions to figure out what specific chip we might be looking at. And so let's take a look at that. As you can see there, going back and forth between the terminal and the PowerPoint's kind of annoying. So I'm going to pull up that STM memory region document real quick. And if anybody has any questions, just drop them in the chat, please. All right. So this URL. Yeah, so the flash, if you're asking when you say locked, the flash on these chips can be locked, and we'll find out if this one is or not. So you can lock the flash memory on these so that you can't get to them. All right, and so if you look at that document, there's regions that have the generic device ID register, which is at this address. So let me copy and paste it here. And so we're going to do MDW, which is the memory display word command, and we'll just look at 4 words there. All right, so we get this for the generic ID, which is probably going to be the same across different STM32 chips. And so, yeah, the DAP information is always there, right? Unless the single wire debug interface is locked out, which it very well could be. So typically, it's rare that you would find the entire interface locked out. There was a question about whether or not it's possible if the chip is locked. Like flash locking and debug port locking are independent of one another. So you can certainly lock the flash without locking out debug ports, and that's that's commonly seen. Hang on. So here's the link. Sorry, I posted it in a DM, not in the chat. My bad, everybody. Here you go. Okay, yeah, so we read from this first region, which is kind of the generic device ID register, and then this next region is defined for STM32F0s and STM32F3s. So we're going to try to read a couple of bytes from that and see if we get anything. All right, so we have nothing there. Okay, so we'll move down the list to the next one, which is 1FFF7E8 for STM32F1s. And we get nothing for that as well. So 1FFF7A10. Okay, so this is for STM32F2s and STM32F4s. And Mike, I knew that address because they're labeled in that header file that I just posted a link to. So those are commonly used addresses for identifying various types of STM32 chips. All right, cool. So we got, we saw that we can read, we actually have something at this address. So between that and what we saw in the ROM table, it's a fairly safe bet that we're working with an STM32F2 series. So now I'm going to go back to the PowerPoint. And so you'll see here, I wanted to include this example as well. You'll get an error if it fails to read memory, if you can't actually read memory from that particular address that you're trying to read from. So someone had asked, what if it's not memory mapped? This is exactly what you're going to get, or what you're going to see. So of all these, only one of them worked, and it was the one that was specified for the F2 and F4 series, so the STM32F2, STM32F4. So yeah, this confirms to us that's an STM32F2 or F4 series. And so luckily for us, the good folks at OpenOCD have a configuration file for that specific CPU. Yeah, and it could also be an L0. That's correct. So someone asked here, F2, F4, or L0. Yeah, it could be any one of those. So if we look in OpenOCD at the config files, we have one for the STM32F2X chip. And so we can include that file with our original config that we wrote in order to get some more information about the chips. Let's do that now. I'm going to take you back to the terminal. So And if you're looking for these config files after you've installed OpenOCD, they're in user local share OpenOCD. All right. So again, as we saw before, the RPI-SWD config is kind of a generic single wire debug adapter config you can use. And I believe that that OpenOCD actually comes with those pre-installed for the Pi. I just wanted to use to write one to give you an example of how they're written and what the various fields mean. All right, so we provide the target STM32F2CFG. All right, cool. So the CPU gets created. Now we have a GDB stub that's available, but more importantly, all the information in that file gives us access to things like the flash commands, and it defines the various flash banks and the various debug peripherals, so we can actually get in there and start interacting with the target chip. So if we go back, now if we do flash banks, right, we can see that we have 2 flash banks, and these are defined in that that config file target stm32f2x-config.config. So we've got the flash memory, and then we've got the one-time programmable memory here. And so that can be dumped to a file. So for those of you that are following along, we can just do flash read bank ID, we'll just give it 0, and then file name, we'll call it bank0.bin. All right, and so again, if the flash in these chips can be configured to be read locked and write locked. So luckily for us so far, we can still read from it, and we'll find out later that it's unlocking these is doable just via a command that OpenOCD provides to unlock the flash, which is nice. It could have been locked in the OTP, and then we would have had to you would have to resort to something like glitching to bypass that. So for these, the flash banks are unlocked, which make it kind of a nice target for learning this kind of stuff. So now if we go back to the PowerPoint, right, we saw that we had 2 flash banks that are available for those of you that are looking at it, and there's additional flash commands which we'll take a look at later on. And you can dump that out with flash read_bank, and then give it the bank ID and the file name that you want to use. And so this is what flash list would give you. And we saw this is reading the bank. And yeah, so luckily for us, which again is kind of why this makes this controller makes for a nice target for learning these kinds of things, is the flash banks here are unlocked, so we're able to read and write to them, which is nice. And so we can read bank 1 and bank 0. If you want to take a look at that, you could look at it in a hex editor. You could do, toss it into Ghidra, whatever you feel like doing. So at this point, we've read, bank 0 and bank 1. Bank 1 being the OTP memory, which is where some of that lockout information would be stored. And so now that we have these two flash banks, you can take a look at it with something like binwalk. You could do hex dump. You could just run strings on it. Because right now this is just a flat firmware image. The format is not necessarily known, but we'll find out later that it is actually defined in an ABI for this chip. But the first step that you want to do with something like this would be to run binwalk or hex dump or strings, what have you. So we'll hop back to the terminal real quick, just take a look at that. And yeah, so someone asked in the chat, what is OTP memory? It's a one-time programmable. So if we just run classic binwalk on it, see what binwalk says, probably not going to get much. Yeah, because this is just a flat memory image. If we run strings on it, bank0.bin, we'll pipe that out to less. Okay, we're not seeing much. This is all kind of garbage, but we are seeing, Xbox input gamepad, PDP gamepad, etc. And so, it's always good to kind of do stuff like this to make sure that you're actually dumping data that makes sense. And that you're, not getting corrupted data or anything like that. So another thing that we can infer, right, if we're seeing plain text strings like this in the firmware image, it's likely not compressed. It's probably not encrypted in any way. And you could use binwalk-e to figure that out. And so we go down and we see, some more of this manufacturer data that we saw when we enumerated the device. And so, yeah, it looks like we've got a relatively complete image of the flash by just using the flash commands in OpenOCD, which is kind of nice. So let's go back to the PowerPoint. And so, yeah, this, these strings here let us know that, one, the data is probably not encrypted or compressed in any way. And these also would be, kind of good candidates for if we wanted to try to rewrite or patch the firmware, this would be something we could change to kind of get a visible result. But as has been mentioned in the chat, STM32 chips can protect and lock these flash banks. And you can also prevent readouts as well. And also when you are writing to these flash chips, they have to be erased first. It's kind of like if you've ever read to or written from, a SPI flash or an I2C flash. But, OpenOCD has support for halting the CPU, obviously, and then you can try to unlock the flash bank so that it can be read to or written from. And so if you're following along at home, you can now, you can try to patch it and see if there's any changes you might want to make. But to flash your modified image to the STM32, first we would want to halt it, unlock it, and then there's a write bank command which does the erasing and writing for you, and then reset it. And so we can take some time now and try to do that and see if we can change something that we can actually visibly see. So I'm going to switch back. Yeah, so regions of the flash could definitely be encrypted. They could definitely be compressed, what have you. If we look at this in a hex editor, so let me go back to the terminal. If we take a look at this in a hex editor, we're seeing, you can see a lot of, and I know this is probably hard for folks to read. There are like definitely some patterns in this as you take a look at it. So throughout, it doesn't look like, it's compressed. There's not a whole lot, there's not super high entropy here. You see we have like two almost identical strings of bytes. These are all probably, similar instructions that are being run. So yeah, we're not seeing, high amounts of entropy. We're seeing plain text strings in kind of the middle of the memory dump. We're not seeing it, at the header or the footer. So yeah, this would, lead one to believe that it is probably unencrypted. And, I've loaded this up in Ghidra and patched it and modified it, and I can tell you that it's not encrypted in any way. So if we want to, find something that we can modify and change, we've got these strings over here that we saw get, presented when the device was enumerated. And so let's go ahead and change this to, give me 1 second. Always make backups. Yeah, the terminal is browser-based. Use this for a training platform as well, and it just it typically makes life a little easier if you're not streaming to a bunch of people. So go back to where we saw those strings, and we'll just patch those to be something different. And those of you that have read my blog post before are probably pretty familiar with how a lot of this works. So let's do that. So we're going to modify one of these descriptor strings to say, Hackaday Remoticon firmware patches, etc. So I'm going to save the changes. So now let's halt the processor. To STM32F2X unlock bank 0. Failed to unlock device. Do it again and it works. So this is another kind of quirk that you might see when you're doing this with OpenOCD. It does typically fail the first time, and I'm not sure exactly why that is. If there's any OpenOCD experts in the chat that might be able to explain that, that would be pretty cool. But I have noticed that you do have to issue the command twice. But so now that that's done, we can do flash, write bank, and what do we call it, mod.bin. Oh, I forgot the bank ID. So bank 0, mod.bin. Oh no, error writing to flash. Why is that? Failed to get read pointer. All right, so we halt. Unlocked. Oh, I said read bank, not write bank. Gee. All right. Okay. No, yeah. So Enrico, this firmware image is very friendly for modifications. There's not really any checks or anything on it, which is kind of why it makes for a good target for a lot of this stuff and makes it easy for people to hack on. Yeah, there's no checksumming, there's no kind of signature or anything. I mean, it turns out, right, the potential threat model for something like this is not super advanced. They're not really expecting anybody to go digging into it, I don't think, as it's a pretty cheap controller. But even in addition to that, there's also another debug interface that we're going to take a look at later that they left in, which is pretty cool. So we've reflashed our firmware image that we just kind of like patched those strings on. So now let's just exit here. So we've reflashed. Let's kill our OCD thing. We'll do dmessage-w. And so let's re-enumerate our controller and see what shows up. Okay. All right. So the product string is all jacked up. And so I'm pretty sure that's because we're using a different image that I actually wrote a different patch for, which is why that's so messed up. So let's see if we can get around that and fix that. All right. So we'll go back to the slides. Okay. One second. Okay. Yeah, so we were able to reflash and patch it. And so this actually, we weren't able to see the changes that we made because this actually has a different image that I've patched to do some other stuff. So I'm trying to see if I can find the stock image to reflash it. But the main takeaway here is that you can patch this with whatever you want, and it doesn't really do any checks or anything on it. And so for this example here, I had patched it, with Wrongbod's artisanal patches, and I had managed to also spell artisanal wrong. So with that, you can unlock the flashbank, you can modify it, and then you can reflash it, all using, OpenOCD and single wire debug, which is pretty nice. And so, we can modify the flash content. We have full control over what it executes at this point. We could try, if you wanted to try to do something malicious, maybe overwrite some of those strings with format strings, see if anything happens. You have, full debug capabilities over this, so you can single step through instructions. You can, halt it, reset it, grab the register state. Anything you would want to do with, GDB or what have you, you can now do thanks to OpenOCD and single wire debugging. So let's take a look actually at how to do that with OpenOCD and GDB. So we're going to go back to the terminal. Yeah, totally. You could, so Cisco just asked, you could add a Bash Bunny app of some sort. Yeah, you could pretty much do, whatever you want. You have full control over the flash, you have full control over the target. And that's kind of where the magic of hardware debugging play. And yeah, speedrun for sure. So that was actually the reason I tried to look at this before is I was so tired of getting my butt kicked in Marvel versus Capcom. And I wanted to try to write some macros to see if I could get it to work. And I ended up writing something, but even that wasn't enough to help me not be terrible at the game. So that's just, that's just on me. So learned some cool stuff along the way. And I hope that was, useful for you folks as well. What were we were just talking about connecting it up to GDB. So let's take a look at how to do that in the terminal. So again, GDB gives us a GDB stub when we spawn it. So we'll do this again. There we go. And then over here, we'll just type in GDB. And so one thing to note, actually, we're running on a Raspberry Pi, which is ARM. And so typically, if you were trying to run, GDB targeting a remote ARM box, you would need to make sure your GDB was compiled with ARM support or with whatever, architecture you're targeting support. The nice thing about running all this from the Pi is that for ARM targets, obviously that's supported out of the box. So we'll do set architecture ARM. We'll do target, remote, localhost, and the GDB port, as you can see, is on 3333. So we can see right here, the GDB port is on 3333. So, and there we go. So it's telling us, we're executing at 80, our PC is 8002 F66. We can do info reg. Sorry if I could type info reg, and then we'll get all the register information. And then if we wanted to, we can single step. So we're stepping through instructions. If we want to disassemble, we can do X10I at program counter. And so here's the instruction that's getting read. So, and you could use a graphical debugger basically if you wanted to, right? Because OpenOCD gives you a GDB stub with which lots of other tools are designed to interact with. We're using the command line version here because it's fairly easy to get up and running and to use and to kind of demonstrate the capability. So yeah, with single wire debugging from the Raspberry Pi now, we have, complete control over this controller. So you could turn it into really whatever you want, as long as you took the time to, either patch the firmware or write your own firmware. But yeah, so thanks to this hardware debugging port, we can now do sort of whatever we want. So if you wanted to set breakpoints, let's take a look at where we are. Let's look at how many instructions are in front of us. So we're doing X, which is the examine command in GDB, for those of you that don't know, and we're telling it to examine 10. You give it a quantity first, and then you give it a format of what you want to examine. And we are telling it instructions. So we're saying, hey, show me 10 instructions at PC, which is the program counter. So, okay, cool. Here is, the current instruction that we're executing. We saw before that the processor had a certain amount of breakpoints and watch points. So if we want to set a breakpoint, we can now do this. So we can just highlight our address. And so for those of you that have done, exploit development or reverse engineering, what have you, like having this level of debugging is extremely useful, right? Because you have full control over the system. You can, set breakpoints, set memory watch points, whatever you want. So if we do break star and then our address, it's telling us we have a breakpoint at this. And so now if we do continue to ask it to continue execution, bam, we hit our breakpoint. And so again, just to kind of illustrate that now you've got full control over this, controller. That sounded kind of weird, but so yeah, via single wire debug, OpenOCD, you now have full control over this thing, and you can reflash it to run whatever you want. You could, try to write macros, try to patch it, etc. So that's a pretty interesting thing, and that's kind of the power of hardware debugging. And we were kind of going from, we were at kind of a zero knowledge point when we started, right? The CPU is covered in epoxy. All we had was the debug port, which, luckily for us was somewhat labeled. And again, as people have pointed out, we are lucky that the flash was unlocked. It totally could have been locked, and that would have stopped us pretty much dead in our tracks as far as only using OpenOCD and the Raspberry Pi. We would have had to resort to something like glitching or some kind of timing attack or something to bypass that setting when trying to access the flash. So yeah, GDB, these are all GDB commands that I'm running. There's some questions in chat about that. GDB also has a disassembler baked into it. So you can tell it like, hey, I want you to disassemble at this address. So what is running on the controller is a bare metal firmware image. It's not an OS. It's not a little RTOS or anything like that. So yeah, these are all GDB commands that are being run right now. And so C is continue, and so we're still hitting this breakpoint. Yeah, so now we have, full control over the system. We can single step through instructions, no problem. We can examine memory. We can examine instructions. So yeah, at this point, we have full control over the controller. And with that, I'm going to go back to the PowerPoint. The Pi is running the GDB server. That's a great question. So someone is asking, does the game controller have a GDB server running on it? No. What the game controller has, right, is that interface, that single wire debug interface that we are talking to. And that's where the magic of OpenOCD comes in, because OpenOCD knows how to talk to all the internal components, all those internal APs, and spin up the same capabilities that a GDB server would expect. So OpenOCD spins up the GDB server, handles all the memory reads and writes for you, and does all that behind the scenes. So we have to thank the developers of OpenOCD for setting all that up for us, which is really cool. So, you know, we've talked about this. We can patch the firmware, we can do whatever, we can rewrite the flash, what have you, no big deal. So, you know, we can single step debug, which is also great. And we already went through this. We talked about looking at it with GDB. We set a breakpoint, et cetera. I feel like it's easier to show in the terminal versus PowerPoint. So someone asked, is there an advantage to using OpenOCD with the Pi versus JLink? You can use either. I wanted to focus on the Pi because I think it's more accessible, and it's, you know, as far as the end result is a lot of the times it's going to be the same. There are platforms that JLink might have better support for, or baked in support using their software tooling. I like to try to use something that's as configurable as possible, if that makes sense, like the Raspberry Pi, in case you run into like some kind of bespoke feature or some weird quirk that you don't know how to deal with. So I like using the Pi for this, but there's a number of different interfaces you could use for this, and they all kind of have their own pros and cons. So I mentioned before that I bricked one of these on accident. And so what I had done was I overwrote the flash with the wrong file. So I accidentally overwrote the flash with a chunk of a markdown file because I just fat fingered some keys. And so what that did was it caused the STM32 to obviously not enumerate when it got powered up, right? So I reflashed it and I plugged it in and nothing showed up. So because it wasn't getting enumerated, it obviously didn't show up as a USB device. It didn't even show, the single wire debug ports weren't even active because they weren't properly configured by the bootloader. So like nothing had run and things were not working. And so, you know, that happens. Sometimes you fat finger something, sometimes you goof stuff up. But as I was, I'll say it angrily, like trying to plug this thing back in and figure out like, how do I get this stupid thing to work? I found out that this has what's called like a DFU mode that's built into the boot ROM for this exact scenario, for when a big dummy like me goes in and flashes the wrong firmware to it. And this was something I found just a few days ago. So I was excited to be able to toss it in here, which is kind of cool. So if you have one of these controllers at home and you hold these three buttons in while you plug it in, you'll see that something different pops up. So I'm gonna load up dmessage in the terminal window for those of you that can see it, and we're gonna take a look at what that does. All right, so I'm sliding over here to get to my hardware. And so let me flip this around. So it's these three buttons. So if you hold these down, so Spork, I'll show you, we'll go to the hardware view real quick. It's these three buttons. So here, here, and here. So if you hold these three down, and we'll go back to the terminal. So we're gonna hold these three down, unplug the controller. We see a USB disconnect, great. And now we'll plug it in again. We've got a totally different USB device. We see STM32 bootloader, manufacturer ST Microelectronics. And so this was kind of a godsend because I was concerned that I had bricked this, and I use this a lot for courses and training, and I was, you know, somewhat worried that if it's this easy to brick it, it's extremely easy for other folks to brick it remotely. But this DFU mode can be used to reflash the device. And this is what you'll see a lot of times, you know, commercially available like development boards will present this interface. And DFU is a device firmware upgrade. So we'll go back to the PowerPoint. Yeah, so DFU, device firmware upgrade. This presents, you know, a custom USB device that we can interact with over USB to get access to the flash. And so here we go. Like we press these three buttons, and then we see this new STM32 device show up, which is very nice. Someone says the combo is up, up, down, down, left, right, BA, PA. Yeah, not quite. So yeah, this was kind of a neat little Easter egg that they left in there for us. And again, like this controller is not built with a ton of protections, you know, in mind, right? So This is not something you see on a ton of devices. It's not something that's super commonly found in the wild, but it's a good thing to be aware of, right? So you can think of this similar to how, like, you know, certain Android phones or most Android phones, you hold the volume down, it goes into bootloader mode, right? That's used for recovery. That's used for, you know, all other kinds of like reflashing modes or whatever. And this is kind of something similar. And so Brandon says, yeah, except for the auth chip, that's 100% true. These do have an internal authentication algorithm that has to go back and forth with the Xbox One. I looked at that pretty heavily with the 360. I haven't looked at it with the Xbox One, so I'm not quite sure how it's implemented. But basically, what you would do on the 360 is you would capture that authentication. You would capture the, using something like USB proxy, you could capture the authentication request, and then after that, redirect the USB traffic to essentially like another code path. So instead of reading from the controller, you would have like a man in the middle kind of thing that would basically perform the auth, and then you would hot swap over to your custom controller that would send the necessary HID stuff. And that's what most of the commercial stuff actually will do. That's why you have to plug a real controller into it. A lot of the older commercial stuff, because you have to pay money for this like little IC that you solder to your board. And the original Xbox would send you like a nonce, basically. You would send that to the IC, you would get a challenge back, ship that back to the Xbox. And that's how you would keep it from, you know, keep people from making third-party knockoff controllers. And yeah, this controller is a third-party controller. It's not an official Xbox controller. I haven't looked at the official ones, mainly because they're kind of pricey, and I don't feel like breaking something that costs, you know, that much money. But these are a little more expendable. So again, now we have this device in DFU mode. So with that, you can use the DFU util to kind of interact with these. And that's an open source tool that you can use to interact with these devices while they're in DFU mode. And so by passing it the -L argument, you can see the different DFU, essentially like peripherals that are presented. So we can go back to the terminal and do that real quick. So DFU util. All right, so what did I do? Oh, sorry, folks. Give me 1 second. Thought I had already built this. Apparently, I had not. See how well this works. Building something live, I don't understand what could go wrong here. Matt, there's a link to the controller on the Hackaday IO page, and I can post that as well. Just give me 1 second. So yeah, as we watch this go by, I'm happy to answer any questions people have. So is there OTP bootloader reading the pins and jumping to the ROM bootloader, or did they hook the buttons up to the boot pins? Great question, Andy. I don't know, and it's kind of hard to tell because the chip is covered in epoxy. So I can't tell what pins they're connected to. I only know the outcome when you hold those 3 buttons. I wish we had the pin out, right? If we had the pin out and we had the part number, we probably wouldn't be here doing this. So I have to assume the OTP bootloader is jumping to some other internal read-only memory that's usable. All right, so that seems good. Let's build this now. Please don't. All right, looks like we're good. So now if we do DFU util -L, can't open the device, so we have to run it as super user. All right, cool. So now we're seeing these interfaces that are presented. And so these are the different features that if you've ever written code for an STM32, there are options, option bytes basically to configure various things about the processor. There's, feature bytes that you can read and write from, and then the one-time programmable memory that we talked about before. So we also have, access to the internal flash, which is super useful because in my case, when I had reflashed this controller with a markdown file and it didn't run, it was nice to be able to access the flash via this DFU utility. So if you want to read that out, you can do it with the following command. So we can do, let me go back here, dfu util and then, so first of all, we'll give it the alternative number here. So we're going to say if we wanted to read the internal flash, we do -A0 -S and then give it the range. So we see here that it starts at hex 8000000, which makes sense, right? That was about the address range that we saw in the GDB prompt that we were in. So let's paste that. And then the flash size we know from before, but you can also see here that they've got the calculation here. So this 4 times 0.16 kg essentially translates to 0x41234. And then we're going to tell it to upload, which might seem counterintuitive. Upload meaning upload the code back from the device. And let's just call this dfu test.bin. Very creative with our names here. So we'll do that. See, we're uploading the internal flash. Now, if we look at the, let's take a look at the strings of the internal flash just to verify we're actually getting what we wrote to it before. So remember before we changed that string to say, Hackaday-U, Remoticon, what have you. So let's take a look at this, dfu test.bin. Like that, less. And let's go, keep scrolling down. I'm sure this is horrific for those of you that are trying to read this. And so let's see. Back to this. So this is the hex editor in the terminal. Let's go back and see if our changes are still in here, assuming we didn't mess anything up. Oh, interesting. So something got messed up, huh? So it looks like it didn't actually. What did we do wrong? All right, let's take a look at this. So yeah, we read this out, but what we read out is actually different than what we had written to before. I may have, oh crap. Sorry folks, I swapped controllers on you in between. I have 3 of them here on my desk and I grabbed the wrong one. So we read the flash out over dfu util. Someone was asking for the arguments. And the arguments are right here. So the arguments are -A for the essentially like the address or the interface number. So in the -L output, you could see that there were interface numbers that were appended to things. So we have 0, we have 0, 1, 2, and 3. And so -A is for 0, 1, 2, and 3. And then S is the start address and then the size. Upload saying, hey, we want you to upload code to us, and then dfu flash.bin. And so we can use this dfu utility to read out the various flash banks. The alt setting, which is how we tell it what bank we want. The address range, so we give it the range that we care about. And then we tell it, hey, we want to upload the information back to us. And so now we can, write the original image back. We can also erase and unprotect the flash. So I'm going to do that now in the terminal. And if anybody has any other questions, definitely feel free. Yeah, these controllers, someone's mentioning in the chat, these controllers are super cheap used. They're like typically less than $10. So I'm typing in that command now to change that. Okay, and just so you can see what that looks like. So we're telling it, hey, we want to force unprotect the flash region for this interface. And it tells us right here that everything's good. And so when it disconnects, though, that's not necessarily a problem, but we've unprotected the flash. It disconnects, and now it's showing up as the original device again. And let me see if I have a stock firmware image that we can flash to it really quick. Give me one moment. And yeah, any questions, definitely toss them in the chat and we'll get to them. Some people are asking, yeah, so you will notice on the Silk screen, if you have one of these, it does say single wire debug backwards. So if you hold it up into a mirror, you know, kind of like Candyman style, and say its name 3 times, you can also get access to the single wire debug port that way. Just give me one moment here. I'm looking to see if I have a firmware image that we can reflash to it. And yeah, please, by all means, ask away as far as questions go. It is, so Jack is asking, is it internal flash or SPI? It's internal flash. So now, right, if we want to upload a new image, the first thing we have to do is boot it back into DFU mode. So we've unlocked that flashbank. So let's boot it back into DFU mode. Okay, we can see that there, STM32 bootloader. And let's go back here. So now let's take our image that we just read. Let's copy that to readout bin. And let's see if we can change the serial number. So we can see here the serial number is 000FD7C95. So let's see if we can find this. Okay, not found. Great. Probably not true. This is not the best hex editor. I just use it in the terminal so that other folks can see what's going on. So let's see what we can find, if we could find that and change it. See if we can re-upload that. Okay. Yeah, so this data is all kinds of corrupted here, which is interesting. I'm not sure what I was thinking when I flashed this one. I also may have another stock one somewhere. So let me see. Give me 1 second. Let me see if I have another stock one that we can grab since we've got a little time. All right, folks, we're in luck. We've got a stock controller. So running a stock tune. All right, so let's go ahead. I'm going to connect that one up. So yeah, you guys are at the hardware view. Jaren is asking, how did you get started with all this? Do you mean reversing in general or with this controller? Because I had explained before, the controller stuff started because I'm terrible at fighting games and I wanted to try to stand a chance against my friends, and obviously that didn't work very well. Yeah, so I can totally just grab the flash over DFU, and I'm going to do that with this this new stock controller that doesn't have any kind of modifications to the image, so that we can actually see some changes when they happen. So plug this guy in. Let's go into DFU mode. Hold down the buttons. And another interesting thing, if you have this controller, you can when you hold those buttons, it makes the motors rumble. I don't know if you guys could see that on the camera, but it makes the motor rumble, which is kind of an interesting feature. It almost sort of scared me when it happened the first time. I was like, what on earth is this? So yeah, we plugged it in, and again, here it's showing up. So STM32 bootloader. So let's upload it, and we'll do stock firmware.bin. Cool. So we've now read the internal flash. And so One thing that you'll notice if any of you do decide to take a look at this and to modify it, the null termination on a lot of these strings like isn't really properly implemented. So you have to be careful when you're just patching this hex file so that you don't overrun anything. So we know that this shows up. So let's try that again. So we're gonna say hello Hackaday, remoticon, remoticon. Get it together, Matt. And yeah, so then it's gonna say testing controller firmware patches. And then we'll just do bop, bop, bop. All right, so here's our, I didn't realize you folks were looking at the hardware, I apologize. So here's, let me move myself out of the way. So here's our little patch that we're gonna add. And so now let's see if we can flash that. Again, apologies that the camera's kind of all over the place. All right. Yes, save the changes. So now we're gonna unlock the flash. And we're gonna need to, it'll reset itself. So I'm gonna hold the buttons when I run this because it's gonna unlock the flash banks and then do like a soft reset. So we'll do this. Okay. And so let's just double check dmessage, make sure it's showing up. It is, it's showing up as our bootloader device. And so now to reflash a new image, we'll do dash, so defuse address the same, 8 and then 6 zeros, 1, 2, 3, 4, 5, 6. Yeah, the rumble was actually a little jarring. I wasn't sure if the first time it happened, I was just squeezing the controller too hard because I was frustrated. But yeah, the rumble can be very jarring. So we'll do dash D for the target file we want to do, and then mod.bin. So we pulled the stock image, we patched it, and then we are now we unlocked the flash. It reset itself. We put it back into bootloader mode, and now we're gonna push this modified flash image. And yeah, Joseph is saying they probably stored it somewhere. I think he's right, because that same serial number I think does show up in one of the other like OTP blobs, if I recall correctly. So with a dash capital D now, let's see if we can reflash with our mod.bin file. Let's see what happens here. Okay, so first you're seeing that it's erasing. So we talked about that before. We have to erase first, and then we have to write to it. So let this get moving. Yeah, there are a lot of mats in the chat, huh? Yeah, so in general, RE for me, I kind of got started just patching games in college, like older Game Boy games and things like that. I had a lot of friends that were playing emulated versions of Pokemon, and I didn't have the time to keep up. So I was trying to like patch save files so that I didn't have to play as much. Most of my RE initial steps in RE were me just being lazy with games, if I'm being completely honest. But it made it interesting and it made it more fun. So that's why, like, when I teach this stuff, I try to do it through like game consoles and things like that, or console peripherals, smaller game cabinets, etc. So, all right, so we've reflashed it, and now let's try to re-enumerate and see if our changes actually took place. So I'm unplugging the controller now. Plug it back in, so we see USB device. What do we got? Hey, so there we go. Here's our hello Hackaday Remoticon testing controller firmware patches. So we can reflash this via two ways, right? We can do it via single wire debug in OpenOCD, or we can do it via DFU util. And the nice thing about DFU util, I think, as Andy's pointing out here, is if you know how to make it enter this mode, you don't have to solder anything to it. So those of you that have this at home, you don't have to crack the controller open and solder to those pins, because unfortunately with those pins soldered to, you can't close it back up. So now that you have this little bit of knowledge, you can go through and just hold those buttons when you plug it in, and then you can use DFU util to read and write and reflash the firmware. And so with that, I'm going to jump back to the slides. Spork is asking how we learned that it was DFU enabled. It was honestly completely by accident. I was holding buttons down while I plugged it in, and I noticed that it rumbled when I plugged it in. And so it's not an uncommon feature, as other people are saying in chat, to have certain GPIO lines tied to certain boot modes. It's super common in the automotive space. It's common in, I mean, most microcontrollers, right? They can boot up into other bootloader modes in order to, reflash or read firmware. So, oh, it wasn't the rumble that told me it was DFU. It was the fact that it presented itself as, let me go back. We're in the terminal now. So it presents itself as a different device, and that's how it was understood that it was DFU. Yeah, it wasn't I'm not like a rumble whisperer. I didn't know like, oh, it rumbled this many times. This is obviously a DFU rumble. No, it was it showed up because what had happened was because I had overwritten the device with a bad firmware image, nothing showed up when I plugged it in. So I'm, frantically sitting in dmessage plugging and replugging, and then I was accidentally holding those buttons down when I plugged it in and the device showed up. So that was a fun evening for sure. But yeah, as someone mentioned, yeah, hard work to avoid playing. Yeah, that's pretty accurate actually. Working hard to avoid play. So yeah, so let's go back. We'll go back to these slides now. And so yeah, people have asked, yeah, we can pull the firmware over DFU. You can reflash it. We can do basically everything that we can do over single wire debug, except for obviously the image isn't running. So you can't single step through the firmware when it's in DFU mode. DFU mode is used, strictly for reflashing. And it's frankly probably a little safer because you're not running an active firmware image while you're trying to reflash things. If you don't properly halt and try to reflash it, which could have been what happened before when we saw our issues. This stuff never worked. When you're approaching this as a reverse engineer, it's important to remember this stuff doesn't always just work out of the box like it's supposed to, right? You're going to run into setbacks. You're going to have issues. And that's why it's kind of important to understand what these things look like at an extremely low level. And so if you took the Ghidra course that we put together, we kind of architected it such that you had the goal was to give you like a strong understanding of the fundamentals, and it's really no different here, right? So by understanding the protocols and like what to look for and things like that, you're in a better position than just kind of blindly, trying to fire away and get stuff to work. Because 9 times out of 10, the tools are obviously awesome, but they're not designed necessarily specifically for reverse engineering, right? They kind of assume you know a lot about your target. They assume you have the right hardware interface. And a lot of times that's just not the case. So as a reverse engineer, you kind of have to make do with what you have. And what we have are the core fundamentals of the protocol that we've talked about today. And I hope that makes sense. If not, I'm happy to elaborate. I hope that's not too preachy. But so yeah, DFU mode. I can post the command line for this on the course page if people are interested in that. For those of you that have the controller at home and want to take a look at it without soldering and desoldering. And so, yeah, this was interesting. In DFU mode, single wire debug doesn't work. So that's why when I had originally bricked mine, this was super useful. So there may be ways to get it to work in single wire debug. I was unable to get single wire debug working in DFU mode, and I wasn't sure if maybe the port was just disabled. So that was just an interesting thing. But basically, regardless of what state you put this device in, unless you somehow overwrite that core bootloader, which I wouldn't recommend you do, and that may even be OTP, right? There's a good chance that that internal bootloader isn't something you can access anyway. But between DFU and single wire debugging, we have complete control of this controller. So quick recap. The controller has 2 mechanisms through which we can upload and download firmware: single wire debugging and device firmware upgrade, DFU mode. And as was pointed out, there are no protections on the flashbanks. If there were, that would have prevented us from reading or writing. And so luckily for us, that was not the case. And the boot ROM for this particular STM32 has handlers that are capable of jumping into DFU mode, which we found that you could enter by pressing those 3 buttons on the controller. So just a quick quiz. If people want to shout these out in chat, how many lines do you need to implement? Yep, 2. People got it. Yeah, you need 2 lines to implement single wire debug. What determines the direction of data flow in the packet? And I know it's been a while since we looked at the packet, but so yep, header bit, perfect. And so, and this question is probably a little vague, but where does single wire debugging fit in the grand scheme of the DAP that we talked about, right? So how does single wire debugging fit in that equation that we had the DAP, the DP, the AP, right? So Single wire debugging is the hardware interface that's used to talk to these things. Perfect. And so how many types of APs are specified in the ARM debug specification? Oh man, you guys are paying attention. That's awesome. Yeah, so there's two, MEmAP and JTAG AP. And someone asked the flash unlock features, are they available in JLink or OpenOCD? They are available in both, I believe. They both have mechanisms for unlocking flashbangs. Does it require, is it common for DFU buttons to require those and only those? That's a good question. We can find out. Let me, I'll hold down more buttons than those three, and we'll see if it still boots into DFU mode. I have a feeling it will, but could be wrong. And Andy's asking, OpenOCD can use the JLink hardware? Yes, it can. The thing about it is with JLink and OpenOCD, from what I understand, and things may be different, it has a, I don't want to say rudimentary because that sounds condescending. It does, OpenOCD's driver for the JLink adapter, I don't think is able to control it at a super well-defined or like at a super granular way. So they're able to, you're obviously able to do single wire debug and JTAG and things like that, but I think the Seger JLink software is capable of doing more with that hardware than OpenOCD. And that was a long answer to a fairly short question, but yes, you can use it. But some of the more advanced features that you might see in the Seger software, I don't know if those immediately translate over to OpenOCD or not. And I think that's because the driver for that device is closed source, right? So Spork is saying it has its own driver and commands. Exactly. That's why the way OpenOCD interfaces with it is fairly bare bones. So you don't get a lot of those additional features. So I'm going to hold additional buttons on the controller and unplug and replug. So I'm holding the 3 buttons, and I'm going to hold, geez, I'm going to hold down A as well. And let's see in the dmessage window what happens. Okay, we got a USB device disconnect as expected. Yep, still shows up with holding additional buttons. So it looks like it only looks for these 3, which is interesting. Actually, let me see if it only needs 1. I always assumed it was just 3. Oh, interesting. Yeah, okay, yeah, so it looks like it's just those 3. So it only works with the 3, but. So with that being said, we are like right at 7 o'clock, and we just got through a single wire debug. So I don't think we're gonna have time to get through JTAG. So with these last few minutes, we'll wrap up and then take any questions and talk with folks. So, you know, single wire debug is a physical interface that's used to interact with a hardware level debugger. It's commonly implemented on, you know, STM32 and other ARM-based chips. Again, it's the ARM debug interface specification, so it makes sense you'd see it on a lot of ARM chips. And that specification is what defines all of the various hardware components that are utilized by SWD. So the different APs, the DPs, all those acronyms that we talked about before. And so using single wire debug, we can take full control over this target system, but it's important to remember that there are security mechanisms that can be put in place to restrict the level of access we have over single wire debug. And it's extremely common in targets to see the flashbangs be locked. So essentially they'll get locked to where they're like write only. So you have to erase it and then you can write to it, but you can't read from it. And people do that to protect IP, things like that. All right, so any questions? Oh, 4 more hours. Yeah, I can't quite do 4 more hours, folks. I'd love to, but I really can't. But I really hope this was helpful, and I'm sorry that there were some issues with the terminal. I hope that, you know, hopefully in the future I can figure out a better way to do that. My monitors are pretty high resolution, so that's on me. So I apologize for that. I'll try to make that better for the last time. So yeah, I hope that I hope you guys had fun, and I hope you learned something. And yeah, I'll hang out for any questions folks have, happily.
Well, Matthew, I think we're good till 4:50 or 7:15 or 15 more minutes. So you can definitely free up. You've got some time. So
okay, yeah, we can jump. We can start to do the JTAG stuff. for sure. So we can, yeah, we probably won't get into a lot of the tooling and stuff because that takes a fair amount of time, but we can at least go over it if there's no other questions. Doesn't look like there is. Yeah, so for more, material and stuff, check out the GitHub IO page for this class. Some people were asking about the Ghidra course that we put on through Hackaday-U. There's a GitHub IO page for that as well. Yeah, I'll drop some links to that in the chat before it ends. I'll do that right now before I forget. Yeah, in case you aren't completely tired of listening to me talk, here's hours more of it. All right, so here's the Ghidra. Oh, I sent that to Thomas again. I don't know why I keep doing that. I'm sorry, Thomas. I don't know why it keeps defaulting to you. Yeah, so here's the Ghidra course, and here's my other page with various embedded RE musings. Feel free to enjoy that. So yeah, we can jump in. With the time we have left, we can jump into JTAG from kind of a high level. So let's do that. All right. So this is SSD. We're not really worried about this. We're just going to burn through this really quick. We don't care about any of this. All right. So we're going to spend the next couple of minutes just talking about how JTAG works, what it is, what it isn't, things like that. Because it's much like the debug access port, it's an extremely overloaded term, as you'll come to find. So what is JTAG? It's an IEEE spec, Joint Test Action Group. Similar to how single wire debug is a physical specification for interacting with a hardware peripheral, JTAG behaves the same way. It was originally designed to grab I/O levels for different chips and to grab pin states over a small amount of pins. So instead of having to physically test each pin, you could clock signals through this interface and figure out what the I/O state was of every external GPIO pin. Where this gets confusing is that JTAG both defines the the protocol layer specification and the test access port that's used for debugging. So think of that as like the DAP that we talked about before. That's defined in the JTAG specification as the TAP. And so this is where like it can get really confusing, and it's an extremely overloaded term. You hear people talking about like a JTAG'd Xbox and stuff like that. It's like it's not a verb. It's not, it can be very confusing when you first jump into it. Yeah, someone here says JTAG is not JTAG. That's a great way of putting it. So at a minimum, it's made up of these 4 pins. You've got clock, test mode select, TDI, TDO, data in, data out. There's other additional pins that you can add, like real-time clock and tap reset for controlling the state machine. But that is, in a nutshell, what the physical interface looks like. It's typically at least 4 pins. You'll often see a system reset pin connected to this as well. And you'll see, power and ground typically too. So clock is used to control, when data is sampled, how data is sampled. TMS is used to control where we are going in the JTAG state machine. So there's a state machine that the JTAG specification defines that controls what you're writing to, what you're reading from. And we'll show that here in a moment. TDI is used to sample data and write data into the register. TDO is used to read data out. And so a lot of times when you see people talk about JTAG, they'll talk about it acting like a shift register. And that analogy is great if you already understand how it works. But if you don't understand how it works, it's extremely confusing, right? Because you think, well, it's a shift register. I'm just feeding data in and I'm just clocking it back out to me. So what does that mean? What people forget to mention is that they are linked together like a shift register, but essentially you shift data in, navigate the state machine to a different state, then you shift data out. And through doing that, you've changed the data that's going to come back out on TDO. So the TAP, or the test access point, similar to the DAP that we talked about, is what we are going to be interacting with that physical interface. So every internal register access that we're going to talk about can be accessed through what's called the TAP controller. And the JTAG specification defines this state machine and the registers that this controller interacts with. And so everything on top of this, right, memory read, memory write, all the components that we actually want are implemented outside of the JTAG state machine that we're going to talk about. So the core JTAG state machine is used to read and write to a specific set of registers. Now, what those registers do is entirely up to the target chip that you're looking at, and that's where it can get really confusing. And so here's an example of this state machine, right? So we've all seen this diagram, or I assume a lot of you have probably seen this diagram if you've tried to look at JTAG before. And so as far as timing goes and how data is read on through this state machine, data is valid on TDO when on the falling edge of clock in certain IR states. Now, that is a mouthful, right? I don't expect anybody to understand that like right now, and we're going to go through all the states so that you understand what that actually means. Data is not shifted in when this shift state is entered. So you enter the state and then you start, I'm pointing to the monitor like you can see that, I'm sorry. So data is not shifted in this state. Basically, you enter the state and then data is shifted in. And so it is shifted in the exit state. And again, that's a lot to take in. That's a lot of sort of timing stuff and definitions that you're not super quite familiar with yet. So let's just try to get through to the core pieces, which is this. So the JTAG specification in its entirety defines a state machine that you can use to read and write to 2 registers, just 2. There's no apps, there's no DApps, there's none of that stuff. All that stuff gets implemented, at a kind of a different level. But at its core, the JTAG state machine lets you read and write from instruction registers and data registers. Now, when I say instruction and data, I'm not talking about like a Harvard architecture kind of thing, right? There's a register that's used to denote an instruction that's going to take place, and there's a register that's used to provide additional data for that instruction that's going to take place. So think of a read operation, right? What do you need if you want to do a read operation? You need a target address. So you would put in the instruction register the read command, and in the data register, you would put the address you want to read from. And so by writing to those 2 specific registers, you would perform the read and then shift the data back out. And we're going to show an example of how that works. But these registers define how you interact with the tap of the target CPU, right? And so every CPU has essentially a different implementation and different definitions for the instruction registers. Now, the spec defines that ID code is a certain instruction value, and that bypass is a certain instruction value. And so again, we talked about, when you're reverse engineering, you want to boil something down to its core pieces. We know that those 2 things have to be defined in order for the tap controller to be JTAG compliant. So those are the 2 things that we'll focus on. But for now, on the whole, what you guys need to understand is that the JTAG tap controller interacts with 2 registers, the data register and the instruction register. And data is shifted in on TDI, as the name would imply, and it's shifted out on TDO, again, as the name implies. So we talked about the instruction register. And so these are this register is written to tell the JTAG state machine like what operation you want to perform. And so the standard defines the bypass instruction, the EX test instruction, the sample preload instruction, and the ID code instruction. Now, most implementations of this that you're going to look at, you'll definitely see ID code and bypass. The other 2 are a bit more tough to maybe define or see. I'm just saying in the things that I've looked at, ID code and bypass have been the 2 that I've always been able to find. So like I said before, this instruction register is used to determine what operation is actually going to be performed, right? Whether it's a read or a write or, querying the status or what have you. And this is all going to be defined by the CPU vendor. And this is where like black box JTAG reversing becomes pretty difficult, because it is just a black box, right? You write to this instruction register, you write to this data register, and you just try to see what comes out, and you're just kind of hoping for the best. Now, there are tricks that you can do to infer more about what different registers do and how they behave, and we might get to that. We probably won't. But the instruction register is used to tell the tap or the debugging core what you want to do. The data register are used to basically provide additional information to the instruction register. And so this is another thing you'll hear people say, and it's 100% true, but to me it was very confusing initially, was that the instruction register selects the data register. Yes, that makes total sense, but you might think about it too much and think like, well, wait, then why do we even have it if it just picks a data register? Why can't I pick a data register? Well, the instruction register, when that gets selected, that loads up a particular data register. It basically maps to a particular data register, right? So that is what people mean like when they say that the instruction register selects a data register. And so again, we talked about it can be used for things like target address or a target value if you're trying to write. But the data register is, read write. So when you perform an operation and you want to look at the result, you read from the data register for that operation. And I think we'll get to a point where we'll walk through the state machine and this will make more sense. So again, sorry, I'm talking really fast. I'm trying to get you guys through the core pieces here. So I'm sorry. Please toss questions in and I'll answer them at the end if we have time. The state machine defines like the core piece of JTAG functionality. Each node in the state machine has a different purpose, and we'll talk about what those are. TMS is used to basically navigate between these different state machines. And by interacting with the state machine, you get access to those two core registers we talked about, right? The instruction register and the data register. And by reading and writing to these registers, we can eventually perform the desired debug operations that we care about. So, state machine navigation. The state machine is navigated by the clock and the TMS signal. So the clock signals when TMS gets sampled. TMS controls which state in that machine it jumps to next. So every clock cycle, TMS is sampled and the state machine is updated. Now, if there's a tap reset pin that's asserted on a clock cycle, you will jump to the default value for the state machine. You'll jump back to the initial state. So test logic reset, first state in the state machine. This is the reset state for the tap. So this is where it starts. You can get to this state machine from any state by holding TMS high for 5 clock cycles. And this is all defined in the specification. And when this happens, this is important to know. When this happens, the ID code instruction is loaded. So what that means is that the data register now contains the ID code for the chip. And this is what things like the JTAGulator use to try to find the state of the controller, right? Or try to find what pins are what. So essentially the algorithm is you hold TMS high, you clock in, 5 clock cycles, you navigate to the shift DR state and read it and look for an ID code. And there's a really great paper called Black Box JTAG Reverse Engineering. I'll try to grab a link to it and drop it in the chat that defines this very, very well. So let me grab this real quick. It's from I don't want to, if I try to pronounce the author's name, I'll probably butcher it. But here is the link to the paper. And this will cover everything that we were going to cover today. So this is a really great starting point for people that want to learn how JTAG works from like a reverse engineering perspective. And it's a really easy read. It's written really well. It's a great paper. It's really great. Can't recommend it. I really can't recommend it higher enough. Like if you're confused by what JTAG is or what it does, give this paper 2 or 3 reads. And it's very short, but it's really great. All right. Yeah, so test logic reset is the default state of the state machine. And then you have run test idle. This state literally performs nothing. It's just for idling or for waiting. If you're waiting for an operation to finish or something might take a certain amount of time, you can return to that state. So select DR scan. This is basically telling the tap that, or select IR scan. It's basically telling the tap, hey, I want to select the instruction register or I want to select the data register. So if TMS is 1, we go here, and then if we clock 1 again, it goes here. Okay, just so people are clear on how this state machine is navigated. These numbers depict the state of TMS when a clock cycle is read. And I guess with that, I think we're at 7:15. I don't think, yeah, there's so much more to get through. But in a nutshell, there's a lot of it. There's a lot of this, but that is, and so what you might see, let me just real quick before people head out, if you're looking for potential headers, let me switch over to the microscope here. This would be we've got 8 pins here lined up, and there's 4 additional pins on top of it, which are actually used for in-system programming for this particular chip, which is pretty neat. But yeah, you got 4 pins lined up like that. pretty small pitch. Well, it's actually just 2 millimeter. It's not that weird, but yeah, you'll typically see, more than 6 pins for a JTAG header. If the header's not broken out, the minimum amount you need are those 4 pins: TMS, TCK, TDI, and TDO. And so that was the 15-minute speed run of JTAG. I know we didn't really get to everything, but read that paper. That paper is great, and reach out to me on Twitter or wherever if you have any questions about this kind of stuff. I'm happy to help.
Well, Matthew, thank you for presenting such an engaging program for us. There was a lot of information, but you didn't let it become an overwhelming flood of data. And I have to say, you have a great cadence for presenting very technical material. And seeing you breeze through this debugging session, I can tell that you're a very patient person. But I'd like to invite everyone to continue the discussion on the hackaday.io's webpage and its public chat. And I posted it in the group chat on the side here of the Zoom room. And I'd like to say thank you to all the attendees. This is really a community that rallies around sharing knowledge, giving positive feedback. And that's one of the things that's made Remoticon a really great experience. So you'll be able to catch and view the other discussions and videos that you may have missed on Hackaday's YouTube channel. And with that, I'd like to thank everyone for participating in Remoticon. We'll hope to see you again or very soon. So keep a lookout for our social media accounts. And yeah. All right, everyone. Thank you again.
Yeah, thanks for hanging out. Thanks for the questions, everybody. This was great.